This video will demonstrate how to use the real-time analyzer in Dirac. Most information can also be found in the context-sensitive help text by opening the RTA window and then pressing the F1 button. The hardware consists of a microphone connected to a 2755 power amplifier that now serves as a USB audio interface to the PC. We already prepared all hardware by setting the laptop output device as the default for Windows sounds, setting up the sound device in Dirac and calibrating the input level. All of these preparation steps can be found in video 1 of this series. The real-time analyzer or RTA is started by clicking the Lively RTA button. The spectrum window opens, showing channel 1. The channel can be changed in the drop-down list at the right of the toolbar. Another way to start the RTA is by double-clicking a VU meter in the measurement window, for instance that of channel 2, after which the spectrum window will open showing the corresponding channel. We select channel 1 again, which receives a microphone signal. The channel here is displayed as a continuous spectrum which can be changed to full or third octave bands. When a band spectrum is selected, the band levels can be displayed in a continuously updated table. Not available for the continuous spectrum. There are 3 averaging modes available. When set to linear averaging over an interval, the measurement must be started with the start button, runs for the specified averaging time, for instance 2 seconds, and stops automatically. The resulting graph or table displays the average spectrum. Back to the original value. The 2 other modes measure continuously and display a running linear or exponential average to be started by this button and the exponential one. In all modes, a measurement can be started, paused and stopped at any time. 2 additional spectra can be displayed. The reference button displays a captured or user-defined spectrum. We can, for instance, display a previously entered NR30 noise rating curve to ascertain that the current background noise level does not exceed it. Off again. And the maximum hold button displays the maximum values from clicking the button. Updates to the spectra can be stopped temporarily using the freeze button. In the RTA properties dialog box, we can select the continuous spectrum, full or third octave bands, which is the same as we saw before using the toolbar buttons. If a band spectrum is selected, an additional frequency weighted value can be chosen, for example A, which is then displayed at the right hand side of the graph. And back to the original values. The y-axis can have a manually fixed scale, or the minimum and maximum values can be chosen automatically. When the min-max hold option is set, the scale may get larger, but not smaller. The averaging time specifies the recording duration for the interval mode or the time constant for the continuous modes. The FFT parameters affect the resolution and update speed of the spectrum, which will be explained in more detail in the next chapter. In this graph area, the graph color and line width for the different spectra can be set. Now let's focus on the FFT or fast Fourier transform parameters. The real-time analyzer displays spectra of successive slices of the incoming signal, and the length of these slices equals the FFT size ranging from 512 up to 16,384 samples. If we have to examine rapid spectral phenomena, we want a vivid behavior of the displayed spectrum, hence short slices. At a sample rate of 48 kHz, the minimum FFT size only takes 11 milliseconds, enabling a short averaging time and a high spectrum update speed. However, there is a trade-off between speed and accuracy, as the frequency step size is the reciprocal of the slice time. Therefore, to increase accuracy, we would use larger slices, which will work better as the signal is statistically more stable. To demonstrate the effect of the FFT size, we replace the microphone by the onboard generator of the 2755, connecting its line output to the line input, and we turn on the pink noise generator, which produces a steady band-limited noise signal. At the current minimum FFT size, the frequency step size is as high as 94 Hz, which is easily visible in a continuous spectrum starting at the same 94 Hz, while in the band spectra such a large step size covers multiple lower bands, which are therefore obviously not accurate at this minimum FFT size. While increasing the FFT size, so do the minimum averaging time and accuracy of the spectrum, in particular at low frequencies, as will be shown now. At 1024 samples, we have 47 Hz as minimum frequency. Twice as many samples imply a higher averaging time, and 24 Hz as the minimum frequency, and so on. And we can see here a flank occurring, which is getting steeper. And at the maximum FFT size, the frequency step size is as low as 2.9 Hz, representing a high frequency resolution, which is reflected by steep flanks, now accurately displaying the band filter magnitude transfer characteristic of the noise generator. Because of the steady noise signal, this can be made even better visible by choosing a high averaging time of 4 seconds. The flanks are very well visible now. And back to the original values. The FFT basically assumes a periodic signal, and non-periodic transitions between slices will cause spectral disturbances, which can be reduced by windowing out these transitions. To demonstrate the effect of these transitions with the present non-periodic background noise signal, we return to the setup with the microphone and select a rectangular window, which is the equivalent of no window at all. The parasitic spectrum is dominant over the wanted spectrum, and we will now capture it for reference. Neglect the captured mouse click sound. Now the handing window is selected. Resulting in the real background noise spectrum, which is no longer overruled by the unwanted energy from the transitions. In general, even a non-rectangular window will slightly affect the displayed spectrum depending on the signal. Therefore, a window is often chosen either empirically or simply equal to that in previous measurements, for a proper comparison of the results. This brings us to the end of this demonstration. Thanks for watching.